In this video, we'll go through each question step by step in the simulation so you can see what you need to do and where. So for Sky Motion question 1, we're going to be in the Rotating Sky Explorer. If you want to know how it works, then you want to go through and look at the other video. So let's go through and take a look at how to find the answer for the North Celestial Pole at 30 degrees latitude, since that's one that we're given. So first I want to make sure I'm at the right latitude. So I'll change this to 30 degrees. It doesn't matter what my longitude is. And now the next piece that it tells me to do is I'm interested in the North Celestial Pole. So if we take a look at our view here, this pole that goes through here and then comes out the other end, where it encounters the celestial sphere, the big sort of glass ball, near the northern direction, that is the North Celestial Pole. And then where it happens in the southern direction is the South Celestial Pole. So basically we want to add a random star. It happened to pop up over here for me. And now I'm going to move it so it's directly where this North Celestial Pole is. So what I want to go through and do now is write down the azimuth and altitude of that star. We can see that right here in this box. If I were to move the star to a different location, we'd see that those numbers would change. But if I have it centered right there, or as close to it as I can get, I would enter those numbers into my chart. Now you'll see that the chart says it has an altitude of 30 degrees, whereas my simulation here says 30.2. There are going to be small, tiny differences between your numbers and the correct numbers, and that's just going to have to do with the simulation. So just do the best you can, and I'll account for it in the grading. So if we were going to go through and do the South Celestial Pole, we would move that star to be right on that blue line right there, and I can see that the azimuth for this is 180, which for the South Celestial Pole you can see is listed as an azimuth as well. All right, so you'll go through and repeat that for the west point of the horizon, which is over here, the zenith, which is where these two lines cross, the North Celestial Pole at 2 different latitudes, the South Celestial Pole at 2 different latitudes, and the intersection of the celestial equator and the meridian. So the celestial equator is this yellow line here. And this one that goes directly between north and south is the meridian. So the intersection of the two is going to be right there at that location. Now, for question 2, we're going to go through and look at some specific star patterns. So first I'll remove all stars, and then one by one I'm going to add some star patterns. So Big Dipper, Orion, and Southern Cross are the 3 listed in your table. So I'm going to turn on the Big Dipper. And we can see it popped up over here. So what we're going to go through and do here is figure out at what latitudes, so if I change this number or if I move my dot here up and down, at what latitudes will I always be able to see the Big Dipper, sometimes be able to see the Big Dipper, and never be able to see the Big Dipper. So there'll be a range of latitudes for each of those. So let's start with where I can sometimes see the Big Dipper. The way that I like to do this is to turn on the star trails, and we'll turn on the long ones so they stay up a little bit longer. And then I'm going to start the animation. And you can speed up this animation or slow it down if you want. We'll speed it up a little bit. But as I can see, for the latitude that I'm at right now, 30 degrees north, the Big Dipper does eventually go below the horizon. So there is a point of time at this latitude where I will not be able to see it. So that means 30 degrees north falls in the sometimes can be seen category. So basically what I want to do is I want to change this latitude, and I can go up by 5, and actually if I click out of it and just go up or down, it'll move by 5 for me. So I essentially want to move it around until I get to a latitude where I can see it. And so that'll be the dividing line between where I can't, where I sometimes can, and where I always can. So we can see from our lab that that dividing line happens to be 42. So right now I'm at 40, and we can see that it just barely dips down there. There's that little white line that goes below. But if I go up a little bit more, we can see that that now moves up. I'm at 45 degrees. Now it always can be seen. It gets really close to that horizon, but it doesn't actually ever drop down. So if I go through and change this, I can check out 43, see what that looks like. It's pretty close. Let's try 42. Looks like it's really on that line. Try 41. That looks even closer. So it's somewhere around the 41, 42, because we saw that when I was at 40, it was below. And again, a difference of a degree or two is not going to make you get it wrong. So that dividing line between when it can always be seen and sometimes can be seen in the north at least is around 41 or 42 degrees north. So now let's start working our way south. The further south I go, and we can see my dot moving further south here. I was up in North America, now I'm somewhere in the middle of the Pacific, but working my way south, I can see that over the course of 24 hours, I'm able to see the Big Dipper for less and less time. So eventually I'm going to get to a point where I get far enough down where I'll never be able to see the Big Dipper. Even though it's rotating around here, it'll be below my green horizon here. And that's what we want to see. So at 40 degrees south, it just barely comes up. This one little star just barely has a hiccup. And if I start to change this and go to 41, that looks pretty close. 42, we can tell for sure it's definitely below. So it's in the 41 to 42 range south, where it gets to the point where it can never be seen. So that means the range that I just went through and found out that the Big Dipper can sometimes be seen is somewhere between 42 degrees north and 42 degrees south. Now, what's the highest latitude and the lowest latitude that you can have? We can see if we keep going down, the absolute lowest you can go down to is 90 degrees south. At that point, you're standing on the South Pole. The same is true for the North Pole. The highest latitude you can go is 90 degrees north. So this should be able to give you enough information to be able to go through and fill out the table. You'll want to go through each time you switch to the next line. You want to remove all stars and then start with the next star pattern. So Orion would be the next one. We can see it here. And then the third one that you need to go through and do is the Southern Cross, which you can see popping up down here in the southern hemisphere. Now, for question 3, what I would recommend in order to visualize this as best you can, you may be able to tell from the table that you create in question 2, but if not, remove all stars, you can add one randomly, and then move it around until it gets to the azimuth and altitude that you want to examine. But keep in mind that if you change your latitude, that altitude and azimuth will change also. So you may be able to go through and figure out whether star A would be circumpolar. A circumpolar star is a star that never sets, so it's one that can always be seen. Star B is, so you'll want to figure out if star A is circumpolar, if it rises or sets, or if it never rises. So, like I said, based on its altitude and azimuth, you might be able to use the table above to make those determinations, or you can go through and play with things yourself. Just remember that each time you change your latitude, you need to go through and change the azimuth and altitude. So, for question 4, you're going to go through and take a look at a few different latitudes. We'll take a look at 40 degrees north, since that's the one that has some answers already listed. So in this particular question, you're going to go through and figure out what the declination of a star happens to be. So, and it's going to be for different locations. So we'll start with our latitude, 40 degrees north, and the options we have here are North Point declination, circumpolar range, South Point declination, and rise and set range. So to start with North Point declination, that's essentially the farthest north you can be. And you can either move this star by hand, or you can actually enter directly in a 0 for azimuth. That means exactly due north. And if it's right on the horizon, a 0 for that as well. Now 0 and 360 for azimuth are the same thing. So imagine a circle. If you turn around in a circle, you go ahead 360 degrees. So you get exactly back where you started with. So if it turns your 0 into 360 degrees, that's okay. So this star now at this point is exactly on our northern horizon. And so all we want to do now is we want to read off the declination, which is over here, of that star. So right ascension and declination are one way for denoting the location of a star. Azimuth and altitude are a different way of denoting a location of a star. The altitude and azimuth of an object depends on where you are on Earth. If you switch to a different location on Earth, that altitude and azimuth would change. So right now I'm at 40 degrees latitude. If I go to 45 degrees latitude, we notice that my altitude has now changed, even though we're still looking at the exact same object. So altitude and azimuth is a good point of directions to be able to share with people who might be standing right next to you, if you want to point out a specific spot in the sky for them to go through and look, because it's based on your specific location. But an object doesn't move in the night sky just because we are changing our location. So I can change my latitude to go all the way up to 70, and this declination hasn't changed because I haven't moved the star itself. So that's what we're looking for right now. We're looking for that declination. Right ascension and declination are sort of like the longitude and latitude of objects in our sky. So like our GPS coordinates, basically. So let's go back to 40, since that's what this question is about. So we can see that the North Point declination is marked as 50 degrees, plus 50 degrees, so you can't have negative numbers. And if this particular star happened to be any further up in the sky, as I start my animation, I would see that it would be a circumpolar star, meaning a star that doesn't set. And so I can keep moving that star. We'll let it complete its full orbit here. I can move it to a higher declination. We can make it go to 60, and we'll see that that's still the case. I can make it go to 70. It's still circumpolar. I can make it go to 80. It's still circumpolar. And if I go to 90, it's right on that north celestial pole. So that means that for this location, this latitude of 40 degrees north, any object that has a declination between 50 and 90 degrees is going to be circumpolar. So let's go through and repeat this for the southern end of things. So I'll move my star. And again, I can move it either by dragging it, or I can type in 180 for the south and 0 for the altitude. And now we can see that my star is right exactly on the southernmost point on my horizon. So at this location, I can see that my southern point, my south point declination is now negative 50 degrees, just like our lab report says. And if I change this declination to be anything less, I can see that it becomes visible. And anything more, and it becomes not visible. So that means my rise and set range is going to be anywhere between the negative 50 degrees declination and positive 50 degrees declination. If I go too far past negative 50 into negative 60, then I can see that nobody up here is going to be able to see the star. It's always going to be below the horizon. But if it's at a declination of 40 or 30, so forth and so on, I'm going to be able to see it. I can even do 0. I can start going to 10, 20, so forth and so on. And eventually I'll get to that 50 degrees that we were at before, where if I go any more, it's all of a sudden going to be a circumpolar object. All right. So for the next few set of questions, you're going to need to go through and describe what you see. For question 5, we need someone at the equator, which is a 0 degrees latitude. So now we're at the equator. we'll turn off star trails for a moment, and we're gonna just add a whole bunch of stars randomly. You want to have at least 20. You can just click the button a whole bunch of times. And now we're going to start the animation continuously. So what the question is asking you to do is describe the motion you see of those circumpolar stars as seen from the equator. So watch the motion over time. Describe what you see. Describe what, if any, circumpolar stars you see. Describe what they look like. Then you're going to pause it and go to the South Pole. So we'll go 90 degrees, and then we need to change this to south. So now we're down here at the South Pole, and we already have our 20 stars going, so we'll go ahead and start the animation. And now you'll go through and do the same thing. Describe the motion of the stars. Describe what circumpolar stars you see. Describe what those circumpolar stars are doing. And that'll give you the answer to question 6. Then for question 7, you're going to use the answers and the results and the observations you made for questions 4, 5, and 6 to come up with a general rule identifying these 3 declination ranges. The range of declinations where you can always see the stars, the range of declination where sometimes you can see the stars but sometimes you can't because they rise and set, and the range of declination where for your latitude you'll never be able to see those particular stars. All right, so for question 8, you're going to go through again and look at different latitudes, and this one's going to be a little bit harder to visualize, but I'll show you an example so you can go through and get an idea of what's going on here. So for the first one, you're going to want to go back to our 40 degrees latitude. We use that one often because it's fairly close to where we are, and it's fairly close to most of North America. Okay, so we have set our latitude at 40 degrees north, and according to the picture for this first part of question 8, we're going to look in the north direction. So I'm going to move my celestial sphere here so that north is at the top. And actually, in order to make this a little bit easier, I'm going to tilt it down so that I can sort of see through the celestial sphere to see what someone, what that little stick person might see. And I'm actually going to remove or move around all of these stars that are anywhere sort of in my way. I'm going to move them all to that northern side a little bit. And this, hopefully, either that or near the South Pole. And this will give me a clearer view. So you may find yourself needing to move some things around in order to see a little bit better. Okay. So if I start my animation now, and I am going to turn on the star trails again so I can see things a little bit better. If I'm going through and looking at things here, oops, it looks like I missed one. Okay, restart things. So if I go through and look towards the north, then I can see that these stars are making small circles around this point, whereas these stars are making big circles. And if I look at the direction of those, it seems to be going the opposite direction that a clock would go. So they're going counterclockwise above some point here in the sky, which is not all the way up to the top, but it's fairly high up there. And if I spin it, I can see a little bit more where that special point is, because again, that's that North Celestial Pole we talked about. So it's close to halfway up from my view. So that is why you see the drawing the way that you see it on your graphs. So you're gonna repeat this idea, switching to different locations, and you may need to move the stars around so that you can see them better. At 40 degrees latitude, you're going to go through and do, we've already done the north direction, you'll do the south direction. So that'll be spinning things around this way. But again, remember, you need to move the stars to the other side so you can see how they move. East would be looking like that, so we can see that we're looking east. And again, you want to, this one will be harder because they'll be coming from both sides and moving in front of you. So you want to ignore the ones in front of you and only look at the ones behind on the one side. We can spread these out a little bit more. So if I'm looking east right now, I put them all on the same side. So now I can get an idea of what they look like when they come up. They're gonna then come down on my side, which I want to ignore. And then when they go back up on the back side, that's what I want to picture when I'm getting ready to draw my diagram for the east, is right now, what things look like right then. And then for the west, all you have to do is turn it around again so that you're looking at the west. And then you want to repeat that thing, but ignoring what they are when they're on the close side of the sphere from you, and only sort of looking through the sphere to see what it would look like if you were inside of it, where they're coming down there. So you'll do all 4 cardinal directions, north, south, east, and west for 40 degrees latitude. Then you'll repeat it for 90 degrees latitude and for 0 degrees latitude at the equator. And there's another example there for 90 degrees latitude. Now there's 2 more questions that we'll utilize this particular simulation for. In question 9, we're going to go through and look at the angles of these star trails. So what we want to go through and do right now is first remove all the stars, and we'll go through and look at the 40 degrees latitude again, since that's our most common one. We're going to add just a single star right now. You'll have to go and find it. And I want it to be right on the east, right on that horizon. And so I can see right now this star is going to follow that path, so I know it's going to be rising exactly due east, which is what my question is going through and asking for. And then I'm going to click the show angle between celestial equator. Oh, not that one. Yes, sorry. The celestial equator with the horizon. So I can see that it gives me this angle here. And so that's what we see recorded in the table. So you'll go through and repeat this for different latitudes. So for example, if I go to 10, then I go through and see that that angle has changed. So repeat this for the different latitudes that you were given. And then in question 10, use the information that you gathered in your data table to come up with a general rule for determining your latitude by looking at these star trails. After finishing question 10 and starting right before question 11, we're going to switch to a different simulation. This one is Seasons and the Ecliptic Simulator. So you can go through and watch the other video to see how all the different pieces work. Here I'll go through everything question by question. So in question 11, we're going through and looking at different dates throughout the year and looking at where the sun is located. Essentially, its GPS coordinates are one of them, which is the declination of the sun. And we're also looking at where the light from the sun is going to be most direct on Earth and where it will be least direct on Earth. So we'll go through and do this for May 5th, which is the example that was given. So we can slide this along until we get to May 5th. All right, so we're at the right day now. So when Earth is at this location in its orbit around the sun, we've got May 5th. And if we go here and look at this view, I can see my latitude here. And I can go through and change that latitude by moving this little person. If I move close, if I keep my mouse close to the person, it moves very coarsely. If I move my mouse further away, then little motions make smaller changes in that latitude. So if I'm trying to be really accurate, I want to make my mouse go as far away as I can. So the first question, or the first column, is declination of the sun. So the answer for that one is right here, 16.1. You'll see that I have 16.5 written in the lab. Small differences of point whatever are not going to make much of a difference. The next part is where is the, what latitude does this little person need to be in order for the sun's rays to be as most direct as possible? So most direct means as close to up and down as you can possibly get. You may not be able to find a place where it's exactly straight up and down, but we want to get as close as we can. And another way to go through and look at this is by looking at, can I get the numbers as close right here, the sun's altitude, to 90 degrees as possible? So I'm pretty close right now. Let's see if I can get it exactly at 90. Wrong direction. There we go. Okay, sun's altitude is 90. The observer's latitude is 16.2. So again, 16.2 north, I should say. And so that's what we want to go through and enter into our table for latitude of the most direct ray. And again, the being off by a few points, 16 point whatever, is no cause for concern. The final column is the latitude of the least direct ray. So my little person here can't move past the North Pole here. They can move down past to the south. So essentially what we want to try and find is, there's two ways of doing this. One, getting it as close to right on the edge of light and darkness as possible. And you may not be able to see this, but there are little tiny lines here going across. They look almost horizontal. It's incredibly hard to see. So a better, easier way to go through and make sure you're in the right spot is to get the sun's altitude right here to 0. So we're pretty close right now. Let's see if I can get it exactly. There we go. All right, sun's altitude is 0. And no worries if you can't get it exact, that's fine too. So the observer's latitude here is what I would put inside of my table for May 5th. And again, 73.9 south is very, very close to 73.5 south. So we are good. So you want to continue this process for each of the dates listed in order to finish question 11. Once you have your table finished, question 12 will ask you to see if you can come up with a general rule that relates the declination of the sun to the latitude where the most direct and least direct rays of the sun are hitting. So basically, do you see a pattern in the declination of the sun compared to the latitude of the most direct ray, or the declination of the sun and the latitude of the least direct ray, once you have that full table filled out? So just write in words what that pattern seems to be. Question 13 is going to compare some specific regions. So your table covers many dates throughout the year and it gives you some various latitudes. So there are specific regions, and we can actually see them here on this Earth. So this is the equator of Earth. And this line up here and this line here designate the tropics. So the Tropic of Cancer is up here. I can move my little person to be on that Tropic of Cancer. And the latitude is 23.5. I haven't got it exact, but you can get pretty close. And then the Tropic of Capricorn is this bottom one, which is 23.5 south. So the area in between these two is what's known as the tropics. So given those two locations and the data that you have in your table, can you find something that makes that region significant? Why those numbers, 23.5 north and 23.5 south? Can you figure out why those seem to be important ones that we want to designate? Question 14 is going to ask essentially the same question, but for the other special region. There's technically two, but in North America, we usually only refer to the one. And that's this line up here. And I'll move this little person up here to it. That's this line right here known as the Arctic Circle. There's an Antarctic Circle down here at the bottom close to the southern hemisphere as well. So again, same as question 13, what makes this region special based from the information you collected in question 11? Now for question 15, Again, you're given a few different latitudes. And you basically want to go through and put your person at each one of those latitudes. So I'll bring my person back and put them on the equator, since that's the one that's already been filled out for you. I'm determined to get it exactly 0. Let's see if I can do it. Done. Excellent. Okay. So because I'm a perfectionist, I wanted to get exactly 0. If you can't get exactly 0, don't worry about it. Get as close as you can. But I can go ahead and start the animation. And so basically, as I watch this animation go through, I've got 3 different views here to focus on. And I want to basically write a short paragraph that describes the pattern of sunlight that I see over the course of the year. So in the description that I provided for you, it talks about the sun's angular height above the horizon. It ranges from 90 degrees, which is what it is roughly right now. It goes down to about 66.5 at its lowest point, and it sort of just goes back and forth between those two. So that's what the first sentence is going through and talking about. It generally describes the fact that they're 66.6.5, and then it starts flipping back. It talks about how on the equator, the sun's light is fairly direct the entire year, which we can then relate to the fact that the equator generally has higher temperatures throughout the year. Once you finish your paragraphs for each of the latitudes listed in question 15, you want to move on to the final simulation to be able to answer the last questions as part of this lab. The final simulation is the Motions of the Sun simulator. If you want to see the specifics of how this works, you want to check out the earlier video. This one will go question by question. So to start, we're going to set a latitude, and there are a few different ways that we can go through and do this. I can spin this around so we can see different views through here. But in order to go through and change the observer's latitude, I want this box right here. That's the easiest way to go through and make these changes. But you'll notice this bar does move when I make changes to that, so you can move the bar as well. But if you want to be as accurate as possible, and the fastest way is just to enter the observer's latitude into that box. So there are a lot of moving parts to this particular simulation, and we're going to use different aspects of it for different questions. For this first one, it's asking us to go through and make some measurements on 3 specific days. So we'll start with the summer solstice. Now I can move this bar along if I want to, or I can quickly jump to specific dates if that's what I'm interested in. So we're going to start with June 21st, the summer solstice. Now, if I go through and take a look at my view here, I can see that the sun is very high in the sky, so this is set right now for 12 p.m. So this is a 24-hour clock. So here's my hour hand pointing at 12 p.m. And it will move forward as soon as I start the animation. So what I want to go through and do is I want to figure out what's the highest point in the sky the sun will get to over the course of this day. So I can change time either by dragging the sun and moving it, or I can start my animation. I can move the clock if I want to, but I just moved it off this line right here, which is what we call the meridian. So it's an imaginary line that connects our northernmost part of our horizon to the zenith, which is right here, the highest point in the sky, back down to the southernmost point. So it divides our sky into the east half of the sky and the west half of the sky. So if I start my animation, we'll see, oops, that's very fast. Let's slow this down. So if I start my animation, I can see as time is going forward, the sun's altitude listed here is becoming a larger and larger number until it reaches this meridian line right here. And then it's going to be at its highest point, and we'll see this number start to decrease. So it's 77.8 right now, gets up to 79 something, and now it starts going down again. So it got up to that 79 something right at noon. So we can go ahead and just always use noon if we want to know what the highest point of the sun is in the sky for that particular day. So I want to write the 79.4, and I've rounded that to 79.5. Again, if you're off by a few decimals, that's not a big deal. So that's what's known as the meridional altitude, basically the altitude of which the object is on the meridian. So there's two other columns there that you need to go through and fill out. One is the rising azimuth, and the other is the setting azimuth. So azimuth is direction. Zero azimuth is north, east is 90, south is 180, west is 270, and then back to north for 360. We can also see that number listed right here. So basically, for the rising azimuth, you want to figure out what direction is the sun going to be at when it's rising on this half of the sky and has a 0 altitude. And the setting one will also be 0 altitude, but it'll be on this side of the sky. And we'll write down that number. So the one that I've already given you is for the autumnal equinox, which is September 21st. So let's go ahead and go to September. And I'm going to move the sun, move forward in time. I'm going to move the sun until it becomes right on this horizon, and I'm going to wait until I get the sun's altitude here to be 0 or as close to it as I could possibly get. All right, so it's exactly 0 now. And so what I want to record in my table is the 270 degrees right there for the autumnal equinox. And I can include the 0.4, but again, if you're off by a few decimal places, that's not a big deal. So you're going to repeat these measurements, 3 measurements for each location. I just showed you how to do the setting one. For the rising one, you would do the same thing. You would just do it on the eastern side. And again, making it go down to 0. These 3 measurements for each of the 3 dates you were given. Once you have those, and you can go through and go back to those 3 dates, you'll want to fill out the figure that's right below the table. To roughly draw out from this view here, so if we turn our celestial sphere, it looks something like this, what the sun's path is for each of these. So that's this line right here that's marked in yellow. And we can actually turn off some of these others if we find that they get in the way. So we want the sun's path right here. So what I'm showing you at the moment is the sun's path for the autumnal equinox. You can go back to June 21st for the sun's path right here. Again, it's the yellow line for the summer solstice. And then December 21st, this yellow line here for the winter solstice. So you want to put each of those 3 paths on your figure. For question 17, it's asking you what would happen if you woke up on July 10th and saw and looked at what the rising azimuth is, and basically asking you how would it change the next day, or 2 weeks later actually is what it says. Would it get bigger? Would it get smaller? Would it stay the same? And you can either use the simulation to help you figure this out. You can use your table, your paths, whatever works best for you. For question 18, we notice that the highest point that the sun got over the course of the year was the 79.5. So at what latitude do you have to get the sun at some point throughout the year to be at a 90-degree altitude? So there are a number of ways you can do this. I would recommend starting at noon, since that's when the sun is going to be highest in the sky. Spinning it around so you can see things. And basically, as you go through and change this latitude, where do you have to make it to go to 90 degrees right here? And does it matter what time of year you're looking at? Are some times of year more likely for it to be 90 degrees or less likely? And you just need to go through and find the closest location to us. So closest location to a latitude of 34 degrees north, in which the sun will actually reach 90 degrees on at least one day throughout the year. For question 19, you're going to go through and repeat everything we just did on question 16 and 17 and 18. But you're going to do it for a new location. So we're going to change our latitude and we're going to take a trip to Norway. So we'll go to a latitude of 71. Repeat the same thing that you just did. So we're already on the meridian on June 21st. So you can see our altitude, the 42.4 is already marked on the table for you. Go through and repeat the meridian measurements for each of those 3 days throughout the year. Then the rising measurement and the setting measurement for each of those 3. And don't forget to include your 3 paths, just like we did for the Walnut location. Question 20 is going to ask you, how far do you need to move on Earth to find a latitude where the sun rises every day? Because if you, or when you get to the point in December, you'll see that in December, if you're in Norway, the sun will never rise. So that is a high enough latitude that you can have more than 24 hours of straight darkness. So at what point do I need to, how close can I be to that location in Norway and have the sun actually rise at least a little bit for at least one day? Every day, at least once, at least a little tiny bit every single day. Question 21 is going to have you go through and look at the times at which the sun rises and sets for 4 different latitudes, 0 degrees, 34 degrees, 66.5 degrees, and 90 degrees. So we'll go ahead and take a look at 34 degrees right now. And it's giving you again our 3 special days. So let's go back to June and we'll start at the beginning. So right now I have my clock set for noon, but what we're trying to do is figure out what time it's going to rise. So I could either do this by changing my clock, or I could go back, move my sun until it is rising, so has exactly or as close to it as you want to get 0 degree altitude. We'll stop there. And the time is 4:53 a.m. So I would write 4:53 a.m. in my rise time. And it's a good idea to use a 24-hour time here, since that's what you're given. But if you want to use AM or PM, that's fine too. Next, we're going to repeat this for what time it sets. So we'll grab our sun, move it over to the western side so that it is setting. Again, get it as close to that 0 degree altitude as we can. That's pretty good. And we see that it sets at 1911. So that's 24-hour time. If I want to know what time that is in terms of AM or PM, I subtract 12 hours from it. So 19 minus 12 will give me 7. So that's 7:11 p.m. Now, the final bit is we want to go through and figure out what the total time is. So you'll need to figure out how many minutes and hours are in between those 2 times. But be very careful. You can't just subtract like you might normally, because there are only 60 minutes in an hour. So if I want to go through and figure out how much time is in between those, then I can see that it is going to be somewhere around, let's see, I need to add 7 minutes to 53 to get it to 5 o'clock. And then from 5 to 19, that means I'm adding 14. So that would be 14 hours. And I had 7 minutes, but then I have to have those 11 minutes also. So that should be 18 minutes. Double checking my math in my head. Yes, that sounds good. You might be able to find an online time calculator if this is something that that you're struggling with a little bit. Adding and subtracting time can definitely be confusing, so don't feel bad if you prefer to use an online calculator or even use it to check yourself. Perfectly okay, but do remember at least 60 minutes in an hour, so you can't just subtract it like you might 1,911 minus 453. That's not going to work. Okay, so you'll repeat the same process for each of those dates and latitudes that's given in the table. And then question 22, your final question for this lab, is basically to look over all of the questions that we've done for this Motions of the Sun simulator, and think about whether or not we should refer to sunlight as a seasonal phenomenon or a daily phenomenon. and why. You want to include your reasons why, and also include whether or not it depends on latitude. Maybe you think that it's seasonal for certain latitudes but not for others. Others, it's more of a daily change. Lots of different possible answers here. It's open-ended on purpose. So just make sure you're clear about not only how you're answering the question, but why you're answering it that particular way. Good luck, and let me know if you have any questions by reaching out on Slack or Canvas.